Okay. Hello, good afternoon. We will wait another minute, see if more folks join in, and then we will start. Thank you for connecting. Okay, let's start. Welcome back. Today is going to be our last session for this fall 2024 session workshops. And today, Enrique will be presenting you the RAG method in order to improve the accuracy of the responses of a large language model. So welcome, Enrique. It's all yours. I'm gonna stop sharing.
Hi. Give me a moment. Okay. I'm going to start sharing my screen.
Yes.
Can you see my screen now?
Yes.
Thanks. Let me make the font a little bit larger.
Yes.
Okay, great. So today's topic is RAG. RAG stands for Retrieval Augmented Generation. And it is pretty popular because it is the de facto way of making an LLM connect to a database to use information to do something, to answer questions, to generate new type of content, or like make summaries, translate stuff by controlling hallucinations. So there's not single RAG official method. Instead, it is, I could say, it's a family of different recipes that approach in general in two ways the synthesis of new text. The first one is the retrieval part, and the second one is the generation part. And we're going to see one example today in which we fetch one article, one PDF, and then we start asking questions about it. So the PDF that we're going to use today is a research paper that came out of Google in 2018. And it's the introduction to the transformers architecture. That is the basics building blocks of GPT-4, Olama, BERT, etc., etc. So you can see that it has many pages, and like usually, like if you want to read it, you need to be like in the know of what is like what's how the math of machine learning is described, and it assumes that it has a lot of knowledge about it. You have as a reader a lot of knowledge about it. So what we're going to do is that we're going to build an AI app that reads this PDF, and then we can start asking questions about it to synthesize. Like, let's say I want to ask a summary, or I want to get the main points, and so forth. And we're going to break down the different steps. How do we approach like getting the PDF? How do we read it? Like, how do we get the text out of the PDF file in a clean fashion? Then how do we create a database with the contents of the text? Then how do we do retrieval? Finally, how do we connect the results of that retrieval into the large language model? So the first step always is that you need to parse your documents. For the sake of today's session, I'm just going to do a single PDF, but this expands to whatever amount of documents you want. This could be in the order of millions. Of course, today is a didactic example. It's a toy example. If you want to do something that scales up, you need to be much more specialized in the sense that you need to apply techniques and optimizations. But the overall big picture will always remain the same. So the way we're going to read the PDF is that we're going to download it directly. So a couple minutes ago, you saw how I opened this URL on Safari. We can use any PDF parsing library. One that I like a lot is called Duckling because it uses multiple different AI models in order to read the text, clean it up, get the tables, get the images, and so forth. And then once you have that parse representation, you can export it into JSON, into Markdown, or get like the actual raw text depending on what do you need. So you can just pip install Duckling and you'll get it, and it's fairly simple to make it work. So we're gonna just run this, in which we are specifying the source, which is the URL to the PDF. We're creating a document converter instance. Then we're using that converter to fetch the source and process it. Once we have the result of the processing, we're going to export that result into Markdown, because Markdown is easy to display and plays nicely with Jupyter notebooks, which is what we're doing right now. So it is done. We have a Markdown cell in which a variable in which we have those contents. And let's just take a peek to it. So the paper title extension is all you need. We have the authors. We have the abstract, which is the summary of the paper, and we have the multiple sections. So you can see that it is formatted such that we have the headers, we have the contents separated in their specific paragraphs. We have some math. Math is not going to be great yet here with Duckling. The way it does it is that it reconstructs the LaTeX. If you're familiar with writing research articles, or you're in physics, maths, or computer science, LaTeX is a format to build documents or to create documents in which you can encode math easily. So it's like programming language, but for creating PDFs or research papers. So this syntax will resemble that. It's not working great yet, but I guess that eventually it will get fixed. And if we scroll down a little bit, we can find tables. So the tables have the results. And it's a lot of information. It is more or less clean, like the text signal we get is good enough. We have the tables, the actual extraction of the tables is great. We have numbers, we have some of the formulas. We can use this to work with. So in the end, Markdown, I'm scrolling down until we finish. But Markdown is just a string that's in a variable. Now that we have that text content out of the PDF, we can start building the Retrieval component. As I was mentioning, the Retrieval component consists of building vector database. You can think about it as a getting that long document and splitting it into smaller chunks, fixed size chunks. So those chunks, the reason why they exist is because we want to focus our attention into specific elements, and the actual LM has a fixed length that can work with. So, I mean, nowadays, like you could use Llama 3.1 or maybe GPT-4o supports super long context windows. But when we're doing RAC, we need to encode these documents into vectors. And some of the most popular models to do this have a fixed size of about 500 different words. So if your document contains 5,000 words, you'll need to split it into 10 chunks. And there are many ways to do this, but one approach that we're going to do is that we're going to leverage the structure of Markdown. So Markdown allows us to mark the headers and the subheaders using pound symbols. So any line that's prepended with 1 pound is going to be a header or a title. And any line that has 2 pounds is going to be a subtitle. So it could be section 2.1 and so forth. So we're going to rely on LangChain that we've been using consistently throughout this workshop series. LangChain has a text processor or text splitter specialized for Markdown. And we're going to specify which headers we want to split on. There are more headers, like you could have triple pounds or four consecutive pounds. We don't want to strip the headers. We want to keep the titles. But anytime that we encounter one header, we're going to split it. So we're going to keep the sections, and that's going to be our chunks. So it could be that once we have those sections split into individual elements, their length still exceeds the 512 token limit. So we're going to use another special text splitter class from LangChain that is going to create a sliding window. So we're going to go through a paragraph and then take the first 512, or actually 250. Then we're going to slide it 30 tokens, take another snapshot, and so forth. So such that we have an overlap. The reason why this is important is because when you're splitting the text, sometimes the answer that you're seeking might lie in between the bounds of the chunks. So you want to keep all that signal together. And if you split it consecutively, you might miss your actual requested information because it's not completely held on either side. So with the overlap, you're giving it an extra chance to keep that text intact. It's not going to be perfect, but it increases the accuracy over downstream. So let's just walk through this code cell. We specify the headers that we want to split on. As I was telling you, just the top level one and the second level type of header. We create the instance of the Markdown text splitter, and we split the Markdown. In this variable, we have a list of the Markdown splits. So instead of having a single Markdown string, we're going to have a sequence of Markdown strings that are going to be documents. Then we apply the recursive character splitter. Basically, what it does is what I was telling you, like it applies that sliding window. We specify what's the length of the chunk and what is the chunk overlap. Then we create that instance, and then we split further the Markdown headers. So in the end, we keep this split. And let's just pick into it. The document class is a LangChain construct, and it has the metadata, and it has the actual contents that we are that we keep on each chunk. So this is the first line, which if I move my window here, you're going to see that at the top, this is like a copyright wording. Then we have attention is all in it. And we have the authors, the list of authors. Then since the list of authors is fairly long, we have another chunk that contains it. Then we have the title of the abstract. And then we have the abstract split into multiple chunks. So if we were to read here, I mean, you can take me by my word, but there will be an overlap here. So we propose here, you see the annotation mechanism.we. So if we go to the end, we can see that there's an overlap here. So that is it. That's pretty much. So then once we have this text broken down, we want to create a vector database. So that's what we're going to do. And before moving to that part, we see that out of a single paper, we end up with 270 different splits. So the next step is that we need to create the vectors. So for that, we're going to use embeddings. You probably heard this multiple times. If you use GPT or OpenAI, you've seen the OpenAI embeddings term, or you've seen sentence transformers or BERT embeddings. they're roughly equivalent. And what we're going to do is that each of these splits that we have, that we just saw, is going to be mapped into a vector. So that vector is going to be used to compute the similarity between the questions and the answers. And we are going to leverage Hugging Face. It's going to do everything for us. And we're going to use a package called Chroma. So Chroma is a vector database. You can think about it as a SQLite, but for, RAG applications. It doesn't require a lot of effort. You just need to have it installed. And you need to specify what is the actual embeddings function that you want to use. I want to highlight this because it is critical that when you're building RAG application, you always use the same embedding model, because otherwise the results, they're not going to crash, but you're going to get garbage results, and you will probably won't know why, because apparently you're doing everything correctly. The reason is that you need to use always the same embedding model or the same encoder, which are synonyms in this context, such that you can compute the similarity between the texts using the embeddings. So we're using Hugging Face, and Hugging Face uses underneath sentence transformers. We don't have to get into the details. What is important here is that we are going to run it, and we're going to add all the splits, the 270, into our vector store. So the result that we see here is a Python list that contains the IDs of each vector. So these are unique identifiers. And what the purpose of the vector database is that we can search for text that is semantically similar. Doesn't have to be precisely string match. So as long as it's related, we'll get something. And I always like to test it to see whether it works. So the title of this paper is "Attention is all you need." So I asked attention is to see what are the top matches. And we have, somehow, well, I guess it's because attention is on the title of this paper from Chris Manning and company. Then we have this subsection that is titled attention, and attention visualizations and so forth. So let's say we want to test soft max. We get the top 4 chunks based on the similarity. What is important here is that this is not necessarily, this is actually not keyword search. It is text or semantic similarity. However, when you're building your own application, you could replace this component by a keyword information retrieval index, such as Lucene or Elasticsearch, or you could do a hybrid approach in which you do a large-scale keyword search and then re-rank it using the semantic similarity. Okay. Something else that you can do is that you see that by default, we get the top 4 documents. We could change that to the top 10 and repeat it. So when you're using LangChain, you can pass parameters to your actual vector database, such as the top K results. You could use a different similarity metric formula, or you could change, any number of hyperparameters. So here, if we ask for attention is after creating a new instance of Retriever that has the top K documents parameter set to 10, we actually get the top 10 results. So say that you want to have a conversation with your PDF, you could do this search, but still the results that you get are not digested. That is where the LM actually comes really, really handy. And what we're going to do is to connect this retrieval component to the generation component. So the generation stands for text generation, which is pretty much ask the LM to do something with it. And for that, we're going to be using Cybersys Verdi AI that has multiple LMs. So we are going to be using Mistral for this, and we just need to create an instance of it. If this is not familiar to you, you can go to the recording of the introduction to LangChain session that we had a few weeks ago, where we go through what is the meaning of this code. But basically, we're creating handle to the LM. That LM is Mistral, and is hosted at Cybers. So that's our AI Birdie infrastructure that we have for AI applications here in campus. I always like to do a test run in which I just ask something to the LM just to make sure that I configured it correctly, because sometimes I forget to set the API key, or sometimes I made a mistake on the name of the model and it crashes. So here, I just plain asked the LM, who are you? And it gave me this answer. So once we are we have our handle to the LM, then it's our responsibility to connect that retrieval component to the LM itself. And this is where things start to get interesting. There's no fixed way to do this, but we're going to use an approach of using a conversation history in which we use a system message to introduce or to fill in the results of the retrieval. And then we use a human message to ask the actual question that we have. So let's just walk through this prompt. The way like you interface with an LM is that you send a sequence of messages, and they are usually interleaved human and AI system messages. But you have always the option at the beginning to add a system message, which is usually used for configuration. So you can configure the LM with, say, saying the role or the persona of the LM, like you're going to be a high school teacher, or you're a journalist, or whatever, like you're a funny guy. In this case, we're going to use it to put in the actual context that is going to be used to answer the question. So you can think about it as, I'm an LM, Mistral, or Llama, or GPT, answer this question for me, but just restrict yourself at using the context that was provided to you as part of your system prompt. Why would we want to do this? Basically, because we want to make sure that any stuff that you tell me, whatever answer you give me, is grounded in something that is real, in the sense that it's written or documented somewhere, and not hallucinated. So when you ask an LLM for something and it gives you an answer, it might as well be correct, but it might also be the case that it's hallucinated. And there's no easy way to tell, because it's going to spit out some phrase or some sentences that like appear to make sense, but it might be factually incorrect. Using retrieval augmented generation, you can instruct the LLM to use just whatever we found in a database that we assume that is created from the beginning to elicit the answer to the question. That is the whole point about it. So it's used to reduce the number of hallucinations and stick to factual stuff. Now, this doesn't mean that it's not going to hallucinate. Sometimes it still hallucinates, and that's where you do prompt engineering, or you try to debug your stuff, because sometimes you ask a question that doesn't have an answer on the database, and you're going to get an empty context. So you need to make sure, like, you need to invest some time on building like safeguards and guardrails. But for the sake of today's session, this is gonna make it just stick in or put in the context and put in the question. So the way to do that is using a chat prompt template. It is a template because we're going to substitute context and we're going to substitute question. And in the end, we're asking the LM to give us the answer. So finally here, what we have is a chain. So a chain in LangChain is a pipeline that we're going to use to configure the data flow. So I'm going to quickly walk through it. We're going to have two branches here. in which we pass the input to that pipeline to context branch that has a retriever that's going to go to the database and fetch the top K documents that are the most similar to the question. And then we're just going to copy that question or that input into the question field. Once this dual branched approach or component of the pipeline finishes, we're going to have two arguments to the conversation template. And you can observe here that the keys of the input dictionary have the same name as the conversation template. So here we're not connecting the LM yet, so we're just going to inspect what are the results. So we're asking what is all I need, and what we get is the two elements. We have the messages, so it contains the context. I'm looking for the key here. Yes, it's right here. So you can see how we start with interpolating the back triple quotes. We have these documents. You can see how like this is serialized as we're taking the whole Python list and we're adding all that metadata that is not really relevant, it's noise. We're gonna fix it in the next couple cells. And down we have the question, which is just copying whatever I had. And this is what we're expecting the LM to respond. So observe how we have all this irrelevant metadata. We need to format it. We don't want like the opening of the list. We don't want the constructor of the class. We don't really care about the metadata at this step. We just want the text. We want this introduction. We have model header, model architecture, and so forth. So we can define a utility to post-process the text of the documents. What we're going to do is that we're going to take each of these documents here, and then we are going to fetch what is the section name, and we're going to fetch the contents of it, and we're going to repeat it. So if we use LangChain again, after retrieval component, we pipe all those results through this format message. So it's going to take that list of documents and it's going to generate a single string. And let's see how it looks now. Okay, so now we got this section 1 introduction, and it's just the title, references. So it's a little bit cleaner, but maybe we could do better later on. Now that we have this, how do I instruct the LM? Or well, actually, we don't want the references. So how can we get rid of those? We can expand this format message utility to make sure that we do not add messages that belong to the references. So we have this control over the retrieval component by inspecting at the metadata that comes out of the vector database. So if we repeat this, we can see that we don't have any reference to the references. Instead, now we have more elements, more splits that contain actual content of the article, like this self-attention, like embeddings and softmax, and so forth. What I asked here was describe the self-attention mechanism. Maybe I can ask what is all I need to see what is the difference. So this Creole only gives us the section titles for any weird reason. But it doesn't really matter. So let's go back to describe the self-attention mechanism. up to this point, we now have a clean signal to send the LM. We're going to send the system prompt message with the context, then the human message that has the actual question and is prompting for the answer. So what we have to do now is to expand our pipeline such that after applying the conversation template, that is piped through to the LM, which is Mistral. And then we get the actual output as a string. And that way we are actually instructing or firing up the generation component of the RAG pipeline. So let's see. What is the description of the self-attention mechanism? Okay, self-attention mechanism, also known as intra-attention, is a method used to compute a representation of a single sequence. By relating different positions within that sequence, it has been successful in various tasks, and you can read this later on. But I can tell you that it is accurate. So what we did here is that we digested parts of the context. But how do I know if this is hallucinated or if it's actually true? One of the potential benefits of RAG is that you can expand the format of the documents that you retrieve, and you can add additional instructions. So I want the LLM to actually quote or refer to the sections of the paper that were used to craft this answer, and we can do that by specifying it in the prompt, basically. So you will not refer to the information. Okay. After you give the answer, cite the section from which you read it. So let's see. This is the difference in the prompt. Let's see what happens if I ask it to describe the self-attention mechanism. Okay. So here, this part came out of section 2 background. This part came out of section 4, why self-attention. Then the complexity of the embeddings comes out of this section, embeddings and softmax. This comes out of section 4. Then we have something else wrong from attention visualizations, input layer 5. I'm not sure exactly what is this. It's probably an image. But you can see now that with these pointers, you could actually go to the paper and decide if you want to dig in or if you want to read it completely. So we can change this. Now, at this point, we're at the stage in which we can do a conversation. You can ask it to do a summary. And it's going to compress a little bit more. You could ask it to do something else, like give me a summary of this work. And I like this example because we are referring to the paper through a pronoun, like this work. We're not specifying that explicitly that there's something behind backing the database, which is the actual vector database that we put together for the splits of the paper. Yeah, summary of this work is not explicitly provided in the given documents. However, based on the information, we can infer all this is giving us the references and so forth. You may be able to play with the prompt to avoid getting this type of messages, like, I couldn't do this, but I did that. You could compel the LLM to just spit out the text without giving any justification. We could also ask like pointwise elements. What are the elements of the transformer architecture? consists of a stacked self-attention and point-wise fully connected layers for both the encoder and decoder. That's correct. It also uses multi-head attention in 3 different ways. Yes, that's correct as well. So this is sort of incomplete, but it's still arguably correct. So in the end, we built an assistant on top of the contents of a document. Now, this could scale. We could have a collection of articles, like say you have a journal or you have database of documents. You can make this scale to the hundreds of thousands or millions of documents. Of course, you'll need the hardware to accommodate for it, but the principle is going to be the same. You can create more complex workflows. You can use this as a component of a wider system in which you get this response and then you enable follow-up questions as a la chatbot, or you can use it to pre-populate different types of stuff. Like if you're like looking at an invoice and you want to ask like who's the buyer, RAG might help you. Or if you ask it like, give me the shipping addresses of all the invoices that occurred within this period of time, RAG might help you achieve that. Of course, you're going to need to do some logic here and there, but the key insight is that you're connecting a database of documents to an LLM to actually do the generations. That is what I think that problem nowadays. 95% of the commercial AI products that you see use a flavor of RAG in some sort of form. It is not that common to use an LLM directly because unless you know the task warrants it, but either you specify some context on the prompt or you connect it to a database like this. Something else that I've seen using a lot is that you connect an LLM to an actual relational database like MySQL or Postgres, and you can query for information such that the LLM maps your question on English or whatever language into SQL, and then you get the results out instead of having to know SQL yourself. And finally, for closing, I wanted to make the optional task of building a UI using Radio on top of this, because like you could be calling this from the Python interpreter, but you also like if you want to apply this, you need to show some sort of user interface. I'm gonna do this on the fly because we still have around 20 minutes. Let's see if we can. I want at the beginning I wanted to do it on a notebook, but it's not working really well. So let's just copy and paste the elements and see if we can make it work on the browser. So we're gonna copy this. Not this. Then we want the vector database. We want to encode the documents. Build your retriever. We want the LM. If you have any questions along the way, please feel free to interrupt me. Then we want the actual pipeline. And I am missing an import statement somewhere. It's missing this as well. We're almost there. Okay. Create this. And then we go to radio. So this is the new stuff. I'm gonna mark it here. Then I'm just going to organize quickly the imports. Okay, I think we're almost there. And then we want an enter point. I need some. Let's see where it crashes. Right now it's creating the vector database. Oh, what happened here? Oh, yes. Let me see. I forgot how we, yeah, sorry, please. Let me quickly Google it. launch. Sorry, we'll have to wait another minute for it to process the PDF and generate the vectors. At least it didn't crash. Okay, so let's go here.
Can you increase the font, please? Yeah, thank you.
Okay. Self-attention mechanism relates different positions of a single sequence to compute a presentation of the sequence. It operates by computing a weighted sum of values at different positions where the weights are computed based on the attendance positions. Yes, this is correct. Abstract of the paper. Okay. So how is this used in machine translation?
There's a question in the chat.
Yes. So Fernando, in a real deployment with many heterogeneous documents, what are some strategies to ensure that chunks extracted contain useful information? How to do quality control in some kind of systematic way? Yes, I think that this is a really important point. So the way we've done it on Verdi is that we have a dedicated software component that handles the intake of documents, and it is customized depending on what is the actual source um, of documents. So it could be PDFs, it could be PowerPoints, it could be Word files, but basically they're split between text files and slide decks. So depending on the text file, it varies a lot on what's the nature. Like sometimes they're very well crafted. Sometimes there are summaries. You cannot do miracles like, for example, in slide decks when they're just like bullet point lists. We cannot infer what is there, but we try to make sure that we have first a high quality PDF parsing component where we handle the noise. Um, Type of noises that you'll see are, say, in PDFs that have a layout of two columns or multiple columns. Sometimes the parser fails and it stitches together all the lines of the different columns as a single sentence. We actually deploy an LLM to help clean that up. Sometimes there are spaces between the characters. So we have identified some of the systemic errors of the components that we have and have deployed mitigations, which are not perfect, but help a lot. Lately, Ducklin, the parser that I showed you here, does an outstanding job at grading research papers. And something else that we've seen is that, say, in syllabi or specific structured documents that we know that they expect minimum default of fields, like, what is the grading criteria or the list of books or assignments. We provide guidelines to instructors such that they follow them if possible, and that we guarantee that in exchange, we're going to give better results. So I guess that if I had to summarize that, is that if you need to spend enough time, probably more, on handling the intake of the documents, looking at the results, and depending on the nature of your documents, you'll need to apply bespoke mitigation of noise. If you have clean signal, then the LLM is going to work really well. I think that the LLM is sort of less than a variable than actually the heterogeneity of the document sources. And there's no one approach. Like, there's no universal approach. It depends on what's the data that you're working with. Okay, so here's telling us the actual motivation behind the self-attention mechanism came from machine translation. So this was one of the earliest efforts, which is so the first pitch was that transformers are parallelizable more easily than recurrent neural networks. This is accurate. So I guess that this is accurate as well. So something to be aware of, like section 23 of Wall Street Journal. This might be hallucinated, but the dataset for constituency parsing also comes from the Wall Street Journal dataset. So you need to be aware of, or be aware of, potential hallucinations when you use this. Another question. Yes, thank you. So the reason why I did this is that I prepared this notebook like a month ago, and before the session, I ran it just to make sure that it worked, and it didn't work. Like, it crashed because two of the libraries we use were updated and the API changed, so I had to fix it. But instead of embedding this into the Jupyter notebook, it didn't work anymore. So Gradio broke its compatibility with Jupyter, so I had to do this. I had to take it off my head right now, but I'm glad that it worked. Yeah, so that's it. So that's pretty much the zero to hero RAG crash course. And like, this is the example. And I always say that when you're doing RAG, doing something really basic is very easy, as you can see, like, relatively, right? But if you want to do this in production grade quality, it is extremely hard, especially because what Fernando, the issue that he raised, getting the data correct is really, really hard. And getting the type of answers that you need might require a lot of trial and error doing your prompt engineering. And sometimes you do actually much more than just RAG. Like, RAG is just a specific piece on a wider system that uses LLMs or different models in multiple places. So that being said, I'll stop sharing here. And yeah, we still have 5 minutes. So if you have any questions, go ahead.
I guess
Thank
not.
you.
Okay, so thanks everyone for connecting, and I'll see you next semester. We will come with new materials and new challenges, and we will continue focusing on AI and ML, especially the use of large language models in many applications. So thanks again, and we'll see you next semester. Bye.
Thank
Take
you.
care.
Thank you.
Welcome.